next speaker is Dr. Marc Kenis, who joins us from CABI in Switzerland. And correct me here if I'm wrong, CABI stands for Commonwealth Agricultural Bureau International, I think so. And so he's based in Switzerland. He got his PhD from University of Brussels in Belgium. His broad area of research is invasive insects, biological control, and parasitoid ecology. In the case of fall armyworm, his focus is on natural enemies and biological control. And he has a side interest in insects as food and feed. El ponente que sigue es el doctor Marc Kenis, quien nos acompaña desde Suiza, donde trabaja en CABI, la Agencia de Agricultura Internacional del Reino Unido. Él obtuvo su doctorado en la Universidad de Brujas en Bélgica. Su área de investigación es insectos invasivos, control biológico y ecología de parasitoides. En el campo de cogolleros se ha dedicado a enemigos naturales y control biológico, y también tienen un interés en el estudio de insectos como alimento humano y alimento para animales. Entonces le paso el micrófono al doctor Kenis.
Okay, thank you very much, Julio, and thanks for the invitation. It's very interesting workshop so far. Yes, the C of CABI used to be Commonwealth, but it has changed about 40 years ago. They kept the acronym, but from time to time they change the signification. For the moment, I think it's a Center for Agriculture and Bioscience International.
Okay, yeah, that's right. You're right.
We used to say CABI. We just say CABI. And since my talk is not very long, I just want to make a 1 minute start with just showing you that farmers in Nicaragua, for example, they also use soil to put in the walls.
Sure.
This is a Nicaraguan farmer. Although he said that now very few do it. But in the past, when he was young and when he was working with his family in this kind of very large public state farms, that's the way they were controlling fall armyworm. There were big trucks coming with sand. Usually it's river sand, and they came with big quantities of river sand, and all the kids and so were putting sand in the walls.
Wow.
But now he says that most farmer thinks it's much easier with insecticides, so they don't do it
of course,
very much.
Yes.
Yeah. Okay.
Thank you.
So
Thank you for that.
This was just a parenthesis. Yes, I'm going to talk about classical biological control of fall armyworm in Africa and Asia, so where it is invasive. There are lots of quotes with me, you will see in the acknowledgement. Yes, just to mention, but of course I don't have the nice slides of Dr. Ferrake with all these flying moss and so on, but just to remind you, the fall armyworm was first found in Nigeria in January 2016, and from there, as you know, it spreads very fast because it flies so far and so on. And so in just 2 or 3 years, it invaded nearly all Africa. So in 2018, it has invaded most of Africa. And now in 2022, it has invaded nearly all tropical and subtropical Africa and Asia. And it is also now present in several Australian states, and even in New Zealand it was found. So it has been extremely fast, and especially in Africa, but not only in Africa, also in Asia, the damage very quickly became disastrous. In the first 2-3 years, 90% or more than 90% of the fields were infested. There were big yield loss, at least at the perception of farmers, and there was a massive use of insecticides. And in Africa especially, farmers are not used to spray insecticides on maize, which is of course a low value crop. So it was really problematic, and it's even more problematic in terms of human health, because they don't necessarily use all the protective clothes and all the necessary equipment for spraying, and of course they also don't necessarily use the safest pesticides. Sometimes they use the leftover of cotton and so on and so on. So it was really bad, especially the first 2-3 years. Now it seems to decrease a little bit for reasons which I will mention later. And so we need new ways of controlling this pest. In most of Africa and Asia, GM crops are not allowed, and insecticide is problematic, as I said. And of course, among the different options, biological control is an option, and especially classical biological control for invasive pests. I just want to remind you what is classical biological control. It is the introduction of a natural enemy of exotic origin to control a pest, usually also exotic, which aims at the permanent control of the pest. So once it is established, the natural enemy, which is a parasitoid, a predator, or sometimes a pathogen, does the work by itself, and there is nothing required by the farmers in the best cases, of course. This implies an important collaboration and work in the area of origin of the pest, or in the country that has already introduced the natural enemy. Also the introduction of exotic organisms, and thus risk assessments and quarantine facilities. You cannot introduce anything. You have to be sure that what you introduce will not cause non-target effects, like for example on native biodiversity. On the other hand, as I said, there is no need for repeated release, which means that there can be huge benefits with classical biocontrol, because the control is continuing year after year without further cost. There are lots of examples in the history of successes in classical biocontrol. When I'm in Africa and when we discuss in Africa, of course, what immediately comes into the mind of the people is the huge success of the cassava mealybug with a parasitoids, which was found in the area of origin of this pest, which was South America. So parasitoid was found in Paraguay, I think, about 10 years after it was introduced accidentally, after the pest was introduced accidentally in Africa. It was a disastrous effect in Africa, because of course cassava is a very important crop pest for millions of families. And this parasitoid alone really saved the cassava production in Africa, and all these millions of families as well, of smallholder families as well. The cost-benefit ratio was used in the 90s. It was calculated to be 1 to 200 to 1 to 500, which means $1 invested brings $500 back. But now it's even more, because it accumulates. Of course, the effect accumulates year after year. And a similar success was obtained in Southeast Asia in 2019, when the same pest was introduced in Southeast Asia. There are lots of other examples in the world. There was some people who calculated that until 2010, there were more than 6,000 introductions against about 700 insect pests, with about 27% of the insect control, but this also includes badly made biocontrol projects. So when the biocontrol project is well done, this rate of success is usually higher. And of course, there are successes in classical biocontrol everywhere. I think one of the latest one in Mexico was the one of the pink hibiscus mealybug by introduction of parasitoids and the ladybird from Asia and from Australia. So now the question is, when you face such a big problem like a fall armyworm in Africa and Asia, can this biological control successes be repeated against fall armyworm in Africa, in Asia, and Australia, where it is invasive? Well, classical biocontrol of fall armyworm is not easy. Because first of all, because fall armyworm is a pest in its area of origin. as we all know. It's a big pest in Latin America. And it's so in contrast to cassava mealybug, for example, which was even not known before it was introduced into Africa. So when it is a pest in the area of origin, it may be more complicated to lower the damage in the region of introduction, of course. Also in America, several publications report relatively low incidence of natural enemies. If you look at the papers, the majority of them report relatively low parasitism rate, and predation is not that much quantified, and so on. Also in Africa and Asia, in contrast to the cassava mealybug, for example, fall armyworm is already attacked by a complex of parasitoids and other natural enemies, as you have heard with Dr. Firake. And of course, if you introduce new natural enemies, they may enter into competition, and people may also wonder why is it worth introducing new natural enemies? Well, I think it's still worth trying to do. First, because fall armyworm is a huge pest with serious impact on livelihoods, including, as I said, human health, because of the suddenly very important amount of pesticide use. And also, even a general decrease of population level by 10–20% would have huge benefits, because it is so widespread in Africa and Asia. Even if you increase parasitism in general by 10% by adding a new parasitoid, you will have a huge effect on a large scale. And also, what is very important with fall armyworm is that, in contrast to other pests, some other pests like fruit flies, for example, you don't need total control. Total control is not necessary because maize plants are relatively resistant, which means that minor damage usually does not result in yield loss. You need quite important damage to have yield losses. And if you can lower the damage below a certain threshold, you may have some damage, but no yield loss. That's why it could be very interesting to just to lower the level of damage. Also, that was my first impression when I first started working on on fall armyworm, is that population levels are lower in the Americas, and the role of natural enemies is probably underestimated in the Americas, I think, as well. I would not say that anymore now, because I think population levels are a bit lower as well, also now in Africa at least, maybe because of the increasing impact of local natural enemies. But still, it's still an important pest. And there are also lots of cases where, following classical biological control, some invasive pests became less damaging in their area of introduction than in their area of origin. So why not trying? Oh, sorry. I took some sounds. I don't know how to. That's another slide. I'm sorry. I will show it like this for the moment. I took it from another presentation. I didn't know there were some sounds. I don't know where to stop this. Anyway, I will show it like this for the moment. So fall armyworm has many natural enemies in America, parasitoids and predators. But predators is not really an option, because predators of fall armyworm are all very generalist. Sometimes against other pests they are not, but in this case they are. So we should not consider them. And then fall armyworm natural enemies in the Americas. There are also many studies and publications. More than 50 parasitoid species are known. Some people say up to 300–400, but of course there are lots of synonyms there. And usually with rather low parasitism, the egg parasitism is often between 0 and 5%. Larvae are often less than 20%. So this is not that promising. But larval parasitism, I think, is often underestimated with fall armyworm, mainly because most parasitoids kill the larvae before maturity. And of course, if you collect the big larvae, you don't get the parasitoids that attack young larvae. On the other hand, the parasitized larvae don't eat very much and are much less obvious to collect. So when you go to the field, you collect those which eat most and which are the biggest ones usually, and these ones are not the ones parasitized. And parasitized larvae and larvae of parasitoids often die in rearing, which means that it's not that you also underestimate parasitism doing sampling this way. So we have fall armyworm. We have egg parasitoids, but I've already seen that during this workshop, so I'm going to go fast here. We have egg parasitoids like Telenomus, like Trichogramma, and then egg larval parasitoids. This is Chelonius insularis, which attacks eggs and come out of the 4th or 15 stars. And then you have early larval and old larval parasitoids, depending on the instars they attack. There are lots of different parasitoids. And then you also have pupal parasitoids, but these are not very well known. These are not well studied. It's much more complicated. So I think now I can go back to the screen. Yes. So what are the main criteria for selecting parasitoids among all these parasitoids in Latin America or in the Americas in general? Well, there are two main criteria. The first is whether it is efficient in all environments. So it's always better to collect the parasitoids which are the most frequent and the most abundant and the most efficient in the area of origin of the pest. That's the first criteria, most important criterion. And the second most important criterion is the specificity, because nowadays it's important to avoid non-target effects in the area of introduction. So the parasitoid needs to be specific. There are also other criteria, like, for example, climatic suitability. But of course, the fall armyworm is so widespread everywhere now in the tropics that you will always find regions that are climatically suitable to a selected parasitoids. Also, it's always better to find an empty niche in the area of introduction. Like, for example, we know that there are lots of different parasitoids already in Africa and Asia attacking naturally the fall armyworm. So it's always better to avoid competition with the new natural enemy. So to avoid introducing species of the same genus, for example. So we selected the most important parasitoids of fall armyworm in the Americas. These are the most frequent ones, the ones which have been most often reared. And we looked at the abundance and frequency, with Chelonius insularis being really the most abundant and frequent parasitoid throughout its range, but some others having also high abundance, and also its specificity, at least in the literature. And for example, the most specific is Aphosoma lafigmae, which is viticole as well. I mean, of course, there are some taxonomic issues there, but it seems to be very specific. And Chelonius insularis and Aleiodes lafigmae being also quite specific according to the literature. And then we also worked with colleagues in Bolivia and Nicaragua, also a bit in Peru and Brazil. And we also looked at what we found in the field in terms of abundance as well. And again, there in Bolivia and Nicaragua, Chelonius insularis was the most abundant one. Aphosoma was very abundant in Bolivia, less in Nicaragua, and so on and so on. So we first selected these two parasitoids for studies. We collect them with the help of our colleagues in Bolivia and Nicaragua. We brought them in the quarantine lab in Switzerland, and we reared them. We observed their biology. We tested their specificity and so on. First, Chelonius insularis, which is the most abundant and frequent parasitoid of fall armyworm in North, Central, and South America. It's the only parasitoid which frequently is reported to reach more than 30% parasitism. I don't want to cite all the studies, but we have studies with high parasitism in Central America, in Florida, also in South America, and so on. But it is reported from several other Lepidoptera in the literature, but about 20 other hosts have been recorded, including 6 other Spodoptera, especially Spodoptera exigua is often mentioned. And we tested quite a few in the labs, and at least 5 species in the lab. And for the moment, they all successfully parasitized in the lab. So indeed, it's not very specific. It is, we first thought there may be cryptic species with high specificity or biotypes, but apparently, at least in the lab, it's not very specific. And also other Kelonius species are important parasitoids of fall armyworm in Africa and Asia. You've heard from Dr. Ferrake that Kelonius formosanus is one of the most important parasitoids in India. But in Africa also, Kelonius bifoveolatus, for example, is also an abundant species. So it is not our main candidate for the moment for introduction into Africa and Asia. The second species is Aphosoma lafigma. It's a big ichneumoniid. It's also one of the most abundant parasitoids in the Americas, but there are regional variations. It's in Brazil, Bolivia, Peru, and so on. That is really the most frequently collected. It's usually the second most abundant parasitoid, with average parasitism of 10–20%, sometimes higher in some fields. So the second after Kelonius, usually. It's also frequent in Central America, also sometimes in Mexico, but it's absent in USA and in northern Mexico, also in Argentina. Maybe because it's too specific, and though in regions in subtropical regions where it's not always present, then it disappears. There is also no congeneric species, so no Aphosoma species on fall armyworm in Africa and Asia, which means that it may compete less with native natural enemies. It's also supposedly the most specific parasitoid of fall armyworm. In the literature, there are only 2 mentions, but of other hosts, but maybe these are errors because these are from a single museum specimens and so on. So we didn't really trust that. And we tested 16 species. And although we found some sometimes female attacking the larvae, there was no development in any of these species. We only got 3 cocoons among several hundred tested from Spodoptera exigua, nothing else. So it seems it's a very specific parasitoid. Yes, that's what we obtained. We also, with the help of our Bolivian colleagues, collected 10 other noctuidae in the surroundings of fall armyworm infestations, including Spodoptera iridana and so on. And Aphosoma lafigma was found only on fall armyworm. This is another way of studying specificity in the field. And this is another sign that Aphosoma lafigma is specific. So now we reach this dilemma here. Should we focus on the most efficient parasitoids or the safest, or both? Well, for the moment, with discussions and so on, although there are some people who want to introduce Kelonius insularis, for the moment at CABI, we are focusing on Aphosoma lafigma. We are writing a petition for release in Pakistan already, because in Pakistan they did other tests. It was also very specific. They established a quarantine rearing there as well, but in Africa so far it failed for some reasons. We have to try again. Rearing methods need improvement because we have really a lot of problem with sex ratio. We have much more males than females and so on. And our rearing is getting old now because it dates from before COVID. So we need fresh material and so on. New strains are needed. So that's it for the moment. We would like to release this Aphosoma next year. We may be interested in another species, Campoletis species, sonorensis or others in the Americas, because we suspect that there may be some of these Campoletis that are 2 or 3 different species, and some of them may be specific. But that's where we are for the moment. So we hope to release this Aphosoma lafigma next year and start with other species. And with this, I stop and I thank our donors, of course. And also, I would like to thank all who contributed to this research in Bolivia, in Nicaragua, and in Brazil, and in Switzerland, in Pakistan, and also for providing test insects. So thank you very much.
Thank you, Marc. Muchas gracias, Marc. Thank you. Very interesting presentation, results, especially for me. Le agradecemos a Marc su participación y abrimos el foro para preguntas. So we're open for questions now. We have at least 5 minutes, so there's plenty of time for questions. So who wants to begin? Okay, so I'll volunteer, Marc. Marc, you mentioned you were having problems with sex ratio in the ichneumoniid and that you were getting male bias ratios. Do you know if there's this CSD, complementary sex determination, going on in the species? I'm pretty sure that's what happens with Kenis. So a word of caution: if you try to rear Kenis on a large scale, you probably will end up with lots of males pretty soon.
Yes.
But do you know if that mechanism is happening in your ichneumoniid?
I don't know. We haven't we have not really studied the mechanism, because we also have the same problem with Kenis, with our Kenis. But the strange thing is that with both species, the male bias sex ratio started at the first generation after we collected them. In the fields, both are 50%, and we immediately had a strongly male bias sex ratio in the first generation. So it's not always easy to study things in quarantine, because we don't have lots of equipment for doing things like we don't have much incubators to put at different temperatures and different light regime, because there may be some simply very simple mechanism as well, simply that the females are just choosing to lay male eggs because they don't like the conditions very much. But we change all the conditions, so
yeah. So a suggestion is to look into the literature for Chelonis, and they do have this CSD, complementary sex determination. And basically what happens is there's a sex determination locus, which operates alongside the haplodiploidy. And when you get a lot of inbreeding, all the homozygotes at the sex determination locus are males.
Yeah.
And so after a few generations, it converts to all males. We've had that problem every time we try to rear Chelonis.
Yeah, but that's why I said that we got this at the first generation. So if it was this phenomenon, I think it would have happened after a few generations, but not at the first generation.
Okay.
And so and with both insects, we had this at the first generation. The first thing that emerged in the lab in both was a strongly male bias sex ratio.
Wow. So these were the field collected ones.
Yes.
Oh my gosh.
No, okay. No. The field collected ones were 50%. Okay. But the first lab generation.
Okay.
I don't think you would have CLT if it's at the first generation. It takes some time. No, I'm not a specialist of that, but I mean.
No, yeah. I mean, if you have a small number of, if your founder population is small, then the inbreeding is probably going to be pretty high at that first generation, because not all females are mating and reproducing, only a subset, and they're probably mating with the same males. And I mean, we've lost our Chelonis populations within 3 generations. They've gone to 100% males. Yeah, so it does happen very quickly.
Yeah.
Yeah, so just a word of caution there. So there's another question here, and it's asking about whether you have measured efficacy in native parasitoids for fall armyworm, I guess alongside the surveying that you've been doing already.
Yes, yes, we have lots of data on the natural parasitism rate. Now, if it means whether they are efficient in augmentative biocontrol strategies, which means mass production and mass releases, we have only worked for the moment at CABI. We have only worked with Telenomus. We don't think that with larval and egg larval parasitoids like Kelonus or with others, we can produce huge amounts, which could be for affordable prices. So it can only be egg parasitoids. But we had an interesting talk at the beginning of the workshop explaining that a trichogramma is very easy, but it's not very efficient alone. And Telenomus, there is a lot of good data of very promising data from Venezuela, but it's not that easy. We worked 2 years on Telenomus, and it was still very expensive to produce in high numbers because it's difficult to produce them on factitious hosts. You still need at least we could not succeed in mass producing them on other hosts like we do with trichogramma, and producing them on Spodoptera remains expensive. And also to release them, the releases were not that successful. I mean, we increased a little bit parasitism, but not that much. What is interesting is that in contrast to the Americas, Telenomus in Africa, and I think also in Asia, can reach very high rates of parasitism naturally without releases. So in several regions, when we survey for egg masses, we find high rates of parasitism by Telenomus. Sometimes 20, 30%, 40% of the egg masses are parasitized by Telenomus, which, as far as I know, never occurs in the Americas if you don't release them. So I don't know if it's because the biotypes of Telenomus or the strains of Telenomus remus in Africa are more efficient than those in the Americas, or whether it is because traditionally African farmers have not used insecticides as much as American farmers. I don't know, but this is very interesting, and it could be studied. I mean, since it is already present, since Telenomus remus is already present with the same, I mean, and genetically it's the same in the Americas, we could also try to see whether the African strains of Telenomus is more efficient naturally in the Americas. I don't know, but it would be worth interesting, at least first in quarantine, to compare the different strains, because I don't understand why otherwise.
Very well. Thank you very much, Marc. I really enjoyed your presentation. As a matter of fact, I'm teaching biocontrol this semester. So as soon as I have the recording available, I'm going to ask the students to listen to your presentation. Lots of good information and insight there. So thank you very much.
I'm sorry for the small things in the middle, because I had taken 2 or 3 slides from another talk, and I had forgotten that these were slides with the sound, with my voice, and I didn't know how to switch this off. So
no, it worked perfectly.
That's why.
Thank you so much.
In the middle, I had to quit the full screen. Yeah.
Very well. All right. Thank you, Marc. Muchas gracias.
Bye.
Dr. Kenis. Bye-bye.